Iñaki, if you can also.
I cannot.
Okay, so great. So it's a fantastic opportunity to hear from Ben Gripaios from Cambridge, who will talk about generalized symmetries of topological field theories. Please take it away.
Okay, so thank you firstly for having me. It's a great pleasure to be with you and able to speak. So today I'd like to describe some work which is currently in progress with Oscar Randal-Williams, who's a mathematician in Cambridge, and Joe Tooby-Smith, who is a physicist now at Cornell. And the basic idea or the goal of the project will be to, can't move my page down.
Yeah,
Sorry.
it says shift page down.
Yeah, so normally when I do it, it should automatically go down, but it seems not to. But I
so
can
maybe
think...
because your screen shared.
Yeah, it's okay. I found a solution to the problem. Okay, so the basic goal of the project will be to try to better understand generalized symmetries of quantum field theories. And you might be thinking, well, we understand those things pretty well already, but I'll tell you in a few minutes' time what I mean by better understanding them. And the idea about how we're going to try to do it is to make two very drastic assumptions. And the first drastic assumption is we will throw away one of the most important structures that a quantum field theory has, which is namely the metric on space-time. And so we will consider instead just topological field theories, which I'm sure you've heard about before. And everything in this talk will be Euclidean topological field theories. So in a sense, the only structure you have is the locality of space-time and a little bit of the quantumness that comes from the fact that you can, let's say, entangle theories. And so that's the first drastic assumption, to go from sort of dynamical quantum field theories to topological field theories. And the second drastic assumption will be to replace the usual symmetries of physics, which are always taken to be Lie groups, that is to say groups with a smooth structure which act smoothly on the things that you're interested in. And just throw that away and just consider the groups, the symmetry groups of physics, just to be abstract groups. And so if you're sort of, if you want an example for which this is no problem, just take finite groups, because there's no difference between the two in that case. But we'll see that groups will appear in this talk, which you might think are Lie groups, but I'm just going to forget about the smooth structure of them. And hopefully it'll be clear later on why I need to do that. So that will be the idea. And there are two fairly drastic steps to take. But what we'll see is that we make a great deal of progress if we make those two assumptions. And so what happens? So basically what we're doing is we're throwing away or forgetting a lot of the structure that theories of physics have. And so there are some advantages and there are some disadvantages. The first advantage is that you can do everything rigorously using the language of categories and functors. And so that's a good thing. And the other good thing is that at least if the space-time dimension is low enough, you can basically compute everything you want to. The bad thing, and it's a very bad thing, is that, as you probably know, when you take topological field theories, you've thrown away most of the dynamics, and so not much actually happens. And so that's, that's a shame, but it's a fact of life. But it actually turns out to be a very good thing when it comes to considering symmetry. You see, because the fewer structures you have in your physical theory, the more symmetry you have. And it's not just that, it's the fact that any structure you might like to add later on, like a metric or so on, well, any symmetry which was there without the structure will still be there, or at least any structure which is present with the structure, any symmetry which is present with the structure must have been there when you didn't have the structure in the first place. So actually, by considering topological field theories, if you're considering their symmetries rather than their dynamics, in fact, you are in a sense in a general case. And anything which is possible to say about symmetries in quantum field theory must be sayable, so to speak, in topological field theory. And so that's what we'll see. There is really a lot of symmetry here. So in principle, I should be able to tell you not only about every possible group, or rather generalized group, that can act on quantum field theories, but I should also be able to tell you, just by looking at topological field theories, every way in which a symmetry group can act on a physical theory. And then the sort of remaining job, if you like, is to add the structures you really want to get dynamics, and then worry about which of those symmetries are preserved. And there's one more bad thing which comes from my second drastic assumption, which is the fact that I'm just going to treat groups as abstract groups. Because those groups don't have a smooth structure, you cannot differentiate them. That means you cannot get something like Noether's theorem. So that goes, and that's obviously a bad thing, but everything else is there. I don't need to say that it would be of great interest to generalize everything I've done to the case in which symmetries are smooth and that you do get the Noether theorem back again. So let me just give you an example of the power of this approach before I get into the details of the talk. If we just consider ordinary symmetries, not generalized symmetries, of a theory which I'm going to call topological quantum mechanics. And what I really mean by that is just topological field theory in space-time dimension 1, that is to say time. And it's going to be a topological field theory which has the sort of most basic structure you could have. That's to say that your time has an orientation. There's a direction of time. So you could, you need that in quantum mechanics to integrate the Hamiltonian, for example. And this topological field theory will be valued in the usual thing, which physical theories are. That is to say, you'll assign a vector space to a point. That's like the Hilbert space of normal quantum mechanics. And to each time interval, you'll assign a linear map, which corresponds to the time evolution operator. So this is just a topological version of quantum mechanics. And let's see what happens. I'll do one more thing, which is, given that I don't have any unitarity or anything like that, I won't work over the field of complex numbers. I'll work over any field K. And as we'll see later on, it actually turns out to be quite liberating to do that. But if you're not happy with it, at any point, you can just set K, the field K, to be the complex numbers and see what you get. And so here's what happens. Dynamically, not much happens. This is all very well known. And in fact, it's so well known that people tend to gloss over one-dimensional topological field theories without really talking about them and get onto the more interesting cases of dimension 2 and higher. But what you have is you have basically every theory is associated to, there's the Hilbert space associated to a point, which is really just a vector space in this context. And every one of those is finite dimensional. That's an immediate consequence of topological field theory. And so every one of them is isomorphic to Kn for some non-negative integer n. And so these theories indeed are pretty boring, because basically the only thing you can measure in such a theory is one number, which is n. There is no more data in the theory at all. But when you look at the symmetries of this theory, there's a lot of possible things. And there must be a lot of possible things because of what I've just said. Every possible symmetry that you could ever have in a theory of quantum mechanics must be in here somehow. And so let's see how it happens. The way it happens is, well, if you're being naive, if you try to guess what a symmetry of this theory would be, once I've told you what the Kn is, once I've told you what n is, then you know what the theory is. And so you might guess that somehow the symmetry is you just look at the automorphisms of Kn. So that, of course, would just be the n by n invertible linear matrices. But it turns out that's the wrong way to think about symmetries of physical field theories. The right way to think about symmetries of quantum field theories is to realize that theories themselves are not sort of isolated entities living out there in their own universe. They form a category. And in fact, we'll see later on, they form a higher category. And so if you want to think about how groups act on quantum field theories, you should think about how groups act on categories. And that leads to sort of much more general things which can happen. And so it turns out that in this special case, in higher dimensions, even more complicated things will happen. The right thing to consider, if you want to consider all the ways that a symmetry can act on a topological field theory, is it turns out that you need to consider not just automorphisms of Kn, you need to consider the automorphisms of the automorphisms of Kn. And this, needless to say, is something which is well studied. So I'm treating GLN as an abstract group, and I'm asking what its automorphism group is. And the answer is that it's basically known, and it's very complicated, but all the possible automorphisms for any n and any k basically break down into one of 5 types. And it's quite interesting to explore what those 5 types are and to see what the connection with physics is. So here's an automorphism you can do. You can take, let me a element in GLN, that's to say it's an invertible n by n matrix. The first thing you can do the trivial automorphism. You can send every matrix to itself. And if you ask what that does, when you think of it as an action on a category, then it turns out to give symmetries, which are just the usual representations of quantum mechanics. So the normal state of play in quantum mechanics is that symmetries act as representations on the Hilbert space. And every single one of those, that's to say, every single group, every single representation corresponds to this trivial automorphism here. And when I say correspond, I'll try to explain later on how you get from one to the other. The next most complicated thing you can do is you can take an inner automorphism of GLN. That's to say, you can just take another invertible matrix L, and you can pre and post multiply by L and its inverse. So that's just conjugation by matrices. if you look at the kind of symmetries of topological quantum mechanics you get by doing that, you get not representations, but you get projective representations. And they are famously important in quantum mechanics. If you take an electron, for example, and rotate it in space, then the electron does not form a representation of the rotation group, it forms a projective representation. An easy way to see that is there are two spin states for the electron, and there are no two-dimensional representations of SO3. And so this is definitely something which is important in physics. And that thing comes out of, it's already present in topological quantum mechanics, as I said it must be. The next kind of automorphism you can do, I've written as sending M to M star, where I mean take the complex conjugate of M. But of course, I'm working here over an arbitrary ground field. So in fact, complex conjugation a priori doesn't mean anything. And what I really mean by star here is that you can do any automorphism of the ground field K. And if you do that to every single entry in your matrix, there are n squared of them, then you get another automorphism of GLN. What does this one do? This gives you the so-called semi-linear representations of a group. And if you take K to be the complex number C, there's basically only one of those that you can do. It corresponds to complex conjugation. Does that have a role to play in physics? Yes, it does. As we all famously know, when you reverse the direction of time, it acts by an antilinear transformation. So that appears in physics as well, as it must. The next thing you can do, the next kind of automorphism you can do is you can send a matrix to its inverse transpose. And remember, there's no unitarity here, and I'm working over an arbitrary ground field. So that is most definitely not the same as just complex conjugating the matrix. And it turns out that this thing also appears in physics in a very interesting way. It appears in physics when you consider it not as a global symmetry, but as a gauge symmetry. And it corresponds to putting non-trivial structures, like a spin structure, on space-time. So physics makes use of this kind of automorphism as well. And then the last thing you can do is you can send a matrix to itself multiplied by powers of the determinant. And that one, as far as I know, maybe you can tell me otherwise, is not actually used in physics. But you see a nice thing, you do this analysis of topological quantum mechanics. I claim that you should be able to see every kind of symmetry that is in quantum mechanics. And indeed, you find that there are 5 possibilities, and nature uses at least 4 of them. But remember now, all we're talking about at the moment, we're just talking about ordinary symmetries. I haven't said anything about generalized symmetries yet. And as you will know, there are no generalized symmetries in quantum mechanics. They're a feature of higher dimensional space-times. But what we would like to do basically is try to do this kind of analysis for generalized symmetries of higher dimensional topological field theories. And that will be what the talk is really about. I should say, by the way, that if anybody has any questions, they should feel free to interrupt and ask. Okay, so the outline will be as follows. That was supposed to be just a sort of taster of what we're going to have. The outline will be, first of all, I want to spend a lot of time talking about what the motivations for this work are, and not just the motivations, but also the conclusions. So basically, I'm going to do the beginning of the talk and the end of the talk at the beginning. And the reason for that is that I want to put off as long as possible doing the next part of the talk, where I'll have to discuss things which are perhaps not as well known as they should be to the physics community, namely not just categories, but higher and in fact infinite categories. And the reason is, as we'll see, that is basically essential if you want to talk about generalized symmetry of topological field theories. So I'll try to explain why just doing the normal sort of mathematics of sets is no good if you want to talk about generalized symmetries. And I'll try to introduce, but admittedly in a very sort of naive way, what infinity categories are. And the thing which is nice is that it turns out that everything that I want to say today in this talk, in fact, can be turned into a question which is not about infinity categories, but it's just a question about homotopy theory. That is to say, the part of algebraic topology where you consider 2 spaces to be the same if they're homotopy equivalent. And so that's a very deep thing, but it's also a very good thing because it means that one can basically compute anything one wants to about generalized symmetries of topological field theories. And so once I've set up that kind of mathematical framework, then I'll be able to talk about what a generalized global symmetry is. I'll talk about generalized gauge symmetries, and then I'll talk about how those 2 things can be connected through the idea of a Hooft anomaly, which you probably all know what it is. and also something which I would like to call a Hooft ambiguity, which, if you like, is a sort of cousin of a Hooft anomaly, which we talk about later, what that actually is. Okay, so let's start with the motivations and the conclusions. So as I said at the beginning of the talk, the idea is to try to better understand generalized symmetries of quantum field theories. And so I should tell you what I mean by trying to better understand. So here is a definition of a Q-form global symmetry in space-time dimension D, which I have lifted verbatim from the original paper of Gaiotto and company. And the definition given there of a Q-form global symmetry is topological operators UG of M associated to codimension Q+1 manifolds that fuse according to a group law. And to me, that already invites several questions about what a global symmetry actually is. So let's ask some questions. Firstly, one of the things this definition tells us is that we get a Q-form symmetry, that is, we get a group for every value of Q between, say, 0 and d-1. And so an immediate question is that all of the structure of a generalized symmetry, or do these groups somehow talk to each other? So that's one question. Is it just a tower of groups, or is there more information? The second question, if you look at the definition that was given there, I was told that the operators had to fuse or had to obey the group law. But as I've just mentioned, the example of rotating electrons or reversing time shows you that there are plenty of symmetries in quantum mechanics which do not behave like representations. And so one would like to learn how to generalize those. The third question I have is that I find this word topological tends to get bandied around in physics rather a lot without people saying what it actually means. And it's not clear to me in this definition what topological actually means. And not only that, it's not clear to me how it's connected with the definition of a symmetry that I learned as an undergraduate. And that definition, the symmetry of quantum mechanics, is just some operators which commute with a Hamiltonian. And so, topological versus commute with a Hamiltonian, they seem to me like two very, very, very different statements. And I would like to understand how one is related to the other. The fourth and last question is, if we have a generalized global symmetry, then what does it mean to gauge it? And if we can gauge it, can we do so uniquely? And again, you might think, well, what kind of a question is that? Everybody knows what a generalized symmetry is, and everybody knows that an ordinary symmetry is gauged by means of a gauge field or a one form, call it what you like. So obviously all we do to gauge a higher dimensional, a Q-form symmetry is to couple it to a higher form gauge field. And I would put it to you, that's most definitely not what it means to gauge a symmetry, because a gauge symmetry, according to me, is to basically equip space-time with a connection on a G principal bundle. And that is the concept which you need to learn how to generalize if you want to talk about gauging global symmetries. And it's not at all clear, at least not to me, the correct way to do that. So here's lots of questions which I think one could better understand about generalized symmetries. And what we'll try to do is answer them all, but in this restrictive context where we have topological field theories and the symmetry groups are not Lie groups, they're just abstract groups. Okay. And so now I'm about to talk about what the actual answers to these questions are in the context of topological field theories. And I write here, do not be alarmed, because I'm about to use some words which probably will only acquire some meaning once we've gone through the middle of the talk. So please remember, this is the end of the talk, not the beginning. And so if you don't understand what a word means, there is at least a chance that it will be explained sometime in the next 40 minutes. Okay, so here is the basic idea. The basic idea is that the one structure, if you like, that you have left in topological field theories is locality. And if you want to enforce locality completely, then what you need to say is that topological field theories are so-called infinity functors between infinity categories. And a miraculous thing happens, which is crucial to all of the results in this work. The miraculous thing is that the topological field theories themselves form what's called an infinity groupoid. So more about what that means in a minute, but the important thing to know is that an infinity groupoid is the same thing as a topological space X. And when I say the same thing, what I really mean is that an infinity groupoid is the same as the homotopy type of a topological space X. So you can think of some space of topological field theories. So you have a set of different topological field theories, you fix the dimension, you fix the structures and so on. What you find is that secretly that whole set of topological field theories is not a set, but it can be thought of as a topological space, or rather homotopy type. So you should think of the different connected components of that space representing different isomorphism classes of physical theories. That is to say, each theory in that connected component will have basically the same predictions for all physical observables. And then the loops in that space will tell you about the automorphisms, the symmetries of those topological field theories. But the key point is that you can think of the space of topological field theories, and by the way, I suspect it's actually true for quantum field theories in general. You can just think of them as a space. And that will be crucial to everything that follows. The next thing that will be crucial is to think of what it means to talk about a generalized group. And the answer will be that a generalized group should be thought of as a one object infinity groupoid. And again, that's not something which necessarily should mean anything to you right now. The important thing is once we pass to homotopy theory, it corresponds to just a space, a topological space, which is not only connected, but it's also pointed. That's to say it has a canonical point in it, chosen point in it, or a base point. And it turns out that every such space, every pointed connected space, corresponds to the classifying space, BG, of some topological group G. And so if you like, you can just think of a generalized symmetry as a topological group. And this is maybe not the best way to do things. And I've written here it's a bit naughty, and I'll explain why it's not the best way to do things later on. But if you're happy with the concept of a group, which I hope most people who are listening are, and if you're happy with the concept of a topological group, then basically you know enough to get through this talk. And in particular, if you start with this topological group and then you say, well, what are these Q-form symmetries? They are just the homotopy groups pi Q of that topological group G. So all of the information that can be stored in a generalized symmetry can basically be stored in a single topological group. And it's crucially important to be able to say this, that I've forgotten the Lie group structure that physical symmetries tend to have. Okay, and so once you know those two things, the rest of it is basically just doing standard homotopy theory in algebraic topology. So for example, if you have this topological group G, which corresponds to your generalized symmetry, then an action of that group on the space of topological field theories is not quite as simple as just a continuous action of the topological group on the topological space X, unfortunately, although that is a large class of examples. What it in fact is, it's a fibration, and it's a fibration over BG with fiber X. And again, they may be things which mean something to you, they may not, but hopefully over the course of the talk, we'll get to understand them a little bit better. So that's just an action of a group on the space of topological field theories. What we really want is to know what a symmetry of a single topological field theory is, and that corresponds to not quite a fixed point of this group action, but a so-called homotopy fixed point of this action. And what that means is basically a fixed point in a homotopy theoretic sense. So if I have a topological space with a point in it, I should consider it as a fixed point under the group action. If that point, it's allowed to move, but as long as the point it moves to is path connected to the original point, then I consider it to be fixed. And another way of saying what that is I said just now that all group actions correspond to fibrations. It turns out that the set of, a homotopy fixed point is just a section of that fibration. And if you take the space of sections, they form also a topological space, which I'm going to call XG. And you should think of that as the space of the original topological field theories, that was X. But now each of those topological field theories, the points in the space, have been equipped with a G symmetry corresponding to this given action. So again, this is a space of topological field theories equipped with a global symmetry G corresponding to the given action. Okay, and so now let's go back to these questions that I had when I was saying that I wanted to better understand what a generalized symmetry is, and let's just answer them all for the case of topological field theories. So the first question was that we have a group, the Q-form symmetry, for all values of Q. Is there any more structure? And the answer is yes, there is a great deal more structure because the Q-form symmetry is just the homotopy, the Qth homotopy group of the topological group G, and that is equal to the Q+1th homotopy group of the classifying space BG, and you get all of the structure which a topological group has. And so in particular, for example, you will find that pi1G, the one-form symmetry group, as a physicist might call it, which is secretly equal to pi2 of BG, must be abelian, because pi2 of anything is abelian. And in fact, that's true for all the higher homotopy groups. And so this corresponds to a well-known fact about generalized symmetries, the fact that their one-form symmetries and above are always abelian. But there's much more structure than that, because, for example, there is an action of pi0G, the naught-form symmetry, on every single Q-form symmetry pi-QG, and that action is the one which is basically induced by conjugation in the topological group. So that's part of the structure you get, and you get a lot more structure besides. So anybody who knows a bit of homotopy theory will know that there is a lot more structure associated with homotopy types. There are things called Whitehead products and so on, and all of those things get inherited by generalized symmetries. Okay, so that answers the first question. What about the second question? How do we see things like rotating electrons or reversing time? How do we get things like projective representations and antilinear representations? Well, it works like this. Every topological space, and in particular, every topological space corresponding to a space of topological field theories, always has the trivial action of any group G, which is just the one where you don't move any of the points of X. And if you take the homotopy fixed points of that action, then you get the usual representations of physics. If you can find any non-trivial actions of your topological group G on X, then you can take the homotopy fixed points of those, and they will give you non-trivial symmetries, if you like. I mean, these ones are still non-trivial symmetries, they just correspond to the trivial G action. You get things like projective representations, antilinear representations, and much more besides. And all of this is now generalized to generalized symmetries, because G is not just a group, it's a topological group. What does topological mean exactly was my third question, and how is that related to the statement that symmetries are things which commute with the Hamiltonian in quantum mechanics? The answer to that question is that a symmetry of a topological field theory is actually a natural transformation in the language of category theory. So what does that mean? The topological field theory does something like the following. In 2 dimensions, it will associate something like a vector space to a circle. It will associate a vector space to the disjoint union of 2 circles. And it will associate a linear map to, say, the pair of pants, which goes between them in topological field theory. And so let's call the topological field theory Z. So if we apply it to all of these things, didn't leave myself enough space. A natural transformation is the following. It is a map of the Hilbert spaces or vector spaces associated to these objects. And it's a map from the functor, the topological field theory, to itself. So this is all just exactly the same as before. And it's just a linear map, let's call it eta G, one for each group element G, such that this diagram commutes. And so this is the linear map which acts on the vector space associated to the circle. This will be the linear map associated to the vector space associated to the disjoint union of 2 circles. And a natural transformation, to say that eta and eta prime are a natural transformation, is to say that this diagram commutes. And if you think about what that actually means, it is literally the statement that eta and eta prime are transformations, linear maps of Hilbert spaces, which commute with all possible evolutions along all possible spacetimes. And that is exactly the same, or rather a dramatic generalization of the statement that h comma u is 0 in quantum mechanics, because this is the same as saying something like e to the iht, applying u is the same as a u and then applying e to the iht. This says that the operator u commutes with all possible time evolutions. The only thing you can do is vary t. Here, what we're saying is it commutes with all possible evolutions. Evolutions now, well, h is 0, there is no dynamical evolution, but the time evolutions correspond to topologically non-trivial spacetimes. And so topological here actually means it's a natural transformation. Okay, and then the last question that I wanted to better understand is how we gauge global symmetries, and if we can do it, whether we can do it uniquely. And so what is a gauge symmetry? I already said, roughly, at least for ordinary symmetries, a gauge symmetry corresponds to taking your space-time M, and there are lots of possible spacetimes, but taking any space-time M and putting on top of it a principal G bundle. And many of you will know that that's the same as supplying a map, or rather a homotopy class of maps from M to the classifying space BG. And now we know what a generalized global symmetry is. It's easy to understand what a generalized gauge symmetry is. We just replace the G here. We replace it, instead of taking a discrete group or an abstract group, we just replace it by the topological group. And all of the things I've just said make sense. And so we have a space of topological field theories, which are equipped with gauge fields, or at least a gauge structure, and they too form a space, which I'm going to call, remember the space of topological field theories was XG. In this talk, I'm going to call the space of topological field theories with a gauge symmetry, I'm going to call it GX, with a subscript in front rather than afterwards. And so you think of that as a space of topological field theories with a background gauge symmetry. And so one of the things we'll show is that there is a map. These two things are topological spaces. There is a continuous map between them, which is called the globalization map. And what it does is it takes, it's the analog, it's the physicist's analog of what the physicist says when they switch off the gauge field. You take a theory with a gauge symmetry, you turn it off, and you get a theory which has got the corresponding global symmetry. And once you recognize the existence of this map, it enables you to phrase the notion of a Hooft anomaly in a very precise way. And it shows you already that there are two possible kinds of Hooft anomaly. And I call them metaphysical Hooft anomalies and unphysical Hooft anomalies. And the reason for the nomenclature will be clear in a minute. Here are two things that can go wrong, basically. One thing that can go wrong is that you can have a theory with a global symmetry, and there simply may be no map which lands on the corresponding space of topological field theories with global symmetry. And if that happens, if there is no map, then indeed you have a Hooft anomaly. That's the first thing that can go wrong, and I call that a metaphysical Hooft anomaly. The second thing that goes wrong is that even if you do have a map, your particular theory, which is a point in the space, may not be in the image of this map. And so I call that an unphysical Hooft anomaly for reasons which will be hopefully clear in a moment. So in mathematical language, the two questions are, does there exist a map to HG, firstly, and secondly, if a map exists, does it surject? And the reason that I call this second type unphysical Hooft anomalies is because of something called the cobordism hypothesis. And the cobordism hypothesis, or rather a corollary of the cobordism hypothesis, says that whenever you consider theories which are fully local, that is to say fully extended in the language of the mathematicians, this map is always a weak homotopy equivalent. And that means that these anomalies of the second kind, so a map which is a weak homotopy equivalence basically is injective or and surjective. And so this second possibility simply cannot occur. And so the Hooft anomalies of the second kind, I call them unphysical because they only happen in theories which have not been defined to be fully local. And so if you like, Hooft anomalies of that kind, which by the way, correspond to many of the ones that we ourselves study, they just correspond to a failure to properly define the theory in the first place. And that's why I call them unphysical anomalies. In my opinion, we should be doing physics or metaphysics, that is to say, studying the real anomalies, the metaphysical anomalies, and not the unphysical ones. If somebody gives you a physical theory, the first thing you should do is ask if it's fully local. And if it isn't, then you should make it fully local before worrying about whether it's got an anomaly or not. Okay, so I spent a long time talking about the motivations and the conclusions, but I did that deliberately, and it's not going to take me long to get through the rest of it. So what we need to do is we need to talk.
Sorry, can I ask a question before you go? When you discussed the gauging, maybe I misunderstood, but I think you're coupling to a background, right? That's the idea. We typically also sum over backgrounds, coupled to invertible faces and so on. So is that implicit in the definition, or?
Yeah, absolutely. So the point is that the space of theories I've got, they're defined on space times equipped with a G bundle. And so, I mean, of course, my groups are abstract groups. So there's a single flat connection. And that, if you like, is the background gauge field. Yeah. And so it's the usual definition of a Hooft anomaly. It's you take a global symmetry and you ask if you can consistently couple it to a background gauge field.
Right. But are you gauging in the sense of summing over backgrounds in this definition?
No. So to me, that would mean, I would call that quantizing, which is to take your background gauge field and make it dynamical by doing a path integral with respect to it. That's a certainly very, very interesting question to ask, but it's a different question. Okay, so let's talk about categories and higher categories, and basically why we need to talk about them to study this problem. And the best way I can think about to justify that is to do a sort of thought experiment in which we try to do physics just using the language of sets. And I'm doing everything rigorously here, so I try to rigorously set up physics just using the old school mathematical language of sets, and we'll see what goes wrong. So here's an idea of what you can try to do. You could say a topological field theory is a function, not a functor, and it's a function which takes you from the set of closed d-dimensional space-time manifolds. So closed means compact without boundary. And I mean, it's true that the closed D manifolds don't form a set, but hopefully you will allow me that. And you could say that a TFT is a function from the set of possible manifolds to the set of complex numbers. And that's all I'm saying there is basically TFT is a partition function. For each manifold M, you give me a complex number, and let's call it the partition function. And the problem with that is you simply cannot do any physics with that information. The point about doing physics is that what you're supposed to do is you're supposed to do some experiments to measure some numbers, and then you relate them to use them to make predictions for other numbers. And if all you've got is a rule which associates to each closed manifold a number, you simply cannot relate one to another. So there is no physics here. And a related point is there's also no locality. See, what you'd like to be able to do to say that a theory is local is you'd like to be able to cut up this manifold and cut it up in multiple ways and glue them together, glue it back together again in multiple ways. And that's what we call, that's what we think of as locality. Notice that when you do that, you don't just get locality, you also get a way to do physics, because if you can cut up manifolds in different ways and insist that the theory is defined on the cut manifolds, then you get relations between the manifolds which are glued together, different manifolds which are glued together in different ways. And that enables you to start doing physics. So in my opinion, no, it's not just that locality is a necessary feature of physics. It's that when you try to rigorously define physics without locality, you don't have physics either. Okay, so quantum field theory or topological field theory with sets, I mean, you can do it, but you don't get any physics out of it. And so let's try to see what the problem is in the language of mathematics. The problem is that if you work using sets and elements of sets, the only thing you can do is you can compare two elements of the set using an equals sign. And that's basically a useless thing from the point of view of physics, because two elements are either equal or they're not. And so if you go to the physics example before, you just get a number for each manifold, and that's all you get. But if you take two sets, then you can do something more subtle, which is you can compare one set with another. You're not allowed to ask if two sets are equal, but what you can do is you can compare them using the functions between them. And those functions themselves form a set, so you can ask if two of the functions are equal. And that gives you a much more sophisticated way to compare two sets. And this is one way of explaining where the idea of a category comes from. You take the sets and functions to be the prototype for a category. And the idea with a category is that it has things which are objects and that they can be compared. You can't ask if one is equal to another, but you can compare them via something called morphisms, which are the generalization of functions, and they themselves form a set. But you don't have to stop there, because once you have a notion of a category, you can ask yourself if you can compare two categories. And the answer is that you can compare two categories using some things which themselves form a category, just as functions formed a set to compare sets. And that category has objects which are called functors and morphisms which are called natural transformations. And let's now go back to physics. And so what we'd like to do is we'd like to have ways of comparing different spacetimes in multiple ways. We'd like to be able to cut manifolds up in multiple ways, not just along manifolds of codimension 1. We'd like to consider manifolds with boundaries and corners and so on. And we'd like to glue them together in all possible ways, because not only will that give us locality, but it will also give us a way to do physics. It will give us a way to relate measurements, numbers, predictions of the theory on different manifolds. And to do that, you need to talk about higher categories. And so you don't just have objects and morphisms, you have objects, you have one morphisms, you have two morphisms, and so on. And so here comes the point, which is sort of, this gets very complicated. It turns out to be better to go all the way to infinity and just forget about the equal sign altogether. And so I'm going to make a definition, which is the key one, which is something called an infinity n category. And an infinity n category has objects, and it has morphisms of all possible levels all the way up to infinity. But the special thing about n is once you go beyond n, every morphism starting from n+1 has an inverse, roughly speaking. And the only other fact we need to know is that you can compare two infinity n categories using another infinity n category, which is basically the functors between them. And that's enough for us to know in order to be able to do physics using infinity categories. But let me first give you an example of an infinity category. And in fact, it's the most important one for this talk. If you take a topological space X, you can make an infinity zero category, which means that all of the morphisms are invertible in the following way. The objects are going to be the points of that topological space. The one morphisms are going to be the paths between any two given points. The two morphisms are going to be the homotopies between any two paths, and so on. And you can see that every one of those are invertible, because if I take a path, for example, I can always go along the path the other way, and that provides an inverse, well, up to homotopy, and that's what inverse means in an infinity category. And so this gives you something for each topological space X, it gives you something called the fundamental infinity groupoid. And the crucial fact, which is called the homotopy hypothesis, is that basically every infinity groupoid arises in this way. So if you're doing something, some physics calculation, and out of it pops an infinity groupoid, you can immediately say, I want to think about that as a topological space. And that's basically what we're going to do with the space of topological field theories. And once you get your topological space out of it, then of course you can compare two spaces. How do you do that? You compare them using the space of continuous maps between them. So basically the strategy is going to be to formulate physics using infinity categories, turn everything into a question about homotopy theory of topological spaces, and then just do a calculation in homotopy theory. And we'll see that turns out to be quite successful. Okay, so let's see how to do physics with infinity n categories. So before I was trying to define topological field theories using sets. And here I'm going to make a new definition. A topological field theory is going to be an infinity n functor. And it's basically going to go through from some category, infinity category, which I'm going to call the Bordism category. And I give it a subscript D and a subscript M. D is the dimension of space-time. N is basically going to be how far down I go in this infinity categorical rabbit hole, so to speak. The objects will be manifolds which are closed at dimension D minus N. And then the one morphisms will be manifolds one dimensional higher with boundary. Two morphisms with manifolds one dimension higher again with corners, until I've got no more manifolds left. And then it will be something like diffeomorphisms, and then isotopies, which are basically homotopies of diffeomorphisms, and so on. So this thing is an infinity n category. And my TFT is going to be a functor out of that to some infinity n category, which I call GKW for God knows what, because one of the problems in this field is deciding exactly what the target category should be. But let's say it's going to extend the usual category whose objects are vector spaces and linear maps, which gives you the usual structure of quantum mechanics. And the most important case is the one in which D equals N, because then you can cut up manifolds in all possible ways. So you basically get all locality, you get all physics, and I will claim that you get all symmetry, by which I really mean generalized symmetry as well. Okay, and so here is a big theorem. I defined a topological field theory to be an infinity n functor. They assembled themselves into an infinity n category, and the big theorem is that that infinity n category is in fact secretly an infinity zero category, that is to say an infinity groupoid, every morphism is invertible, and therefore I can just think of it as a topological space. So as long as I think about topological field theories in the large, in their entirety, I can just treat them as a topological space, or the points of a topological space. And that means I can just do homotopy theory. Okay, so having done that, now I'm able to talk about what a generalized global symmetry is, at least of a topological field theory.
Can I just ask you to go back for a second?
Absolutely, if I can make my page up command work, but let's see.
So this theorem somehow reduces everything to infinity 0, so the TFT d comma n. But
yeah,
those
so
were essentially all invertible, no? You were saying they all had inverses. So even if you started off with something that had non-trivial fusions which didn't have inverses, you get now, you can represent it as something that's purely invertible.
Yeah. So the topological field
on that?
Yeah, absolutely. Yeah. So this is the key point. Okay. The topological field theory itself goes from a very unpleasant infinity n category to a very unpleasant infinity n category, namely boardisms to what I call God knows what. Okay. And those categories most definitely have things which are not invertible. You know, you can draw boardisms between n-1 manifolds which do not have inverses. Okay. The key point is that when each of those TFTs is itself a functor, and you can think of it as an object of a functor category. And so the objects are TFTs, they're the theories. The morphisms are somehow ways to compare two physical theories. And it turns out that every single one of those ways of comparing morphisms is in fact invertible. If you can compare theory A with theory B, you can compare theory B with theory A. And it sounds sort of fantastically complicated, unbelievable. In fact, it's not. The proof basically goes like this. In every topological field theory, for every object, there is a dual object. And so it's basically the same statement, which is that topological field theories in one dimension are finite dimensional vector spaces. That statement, finite dimensional, another way of saying that is it picks out the vector spaces which have duals. And so the fact that you have these dual objects, it basically comes from considering the simplest possible boardisms, which are basically just evaluation and co-evaluation. So go to as many dimensions as you want to, take this diagram in one dimension, and take the Cartesian product with any manifold you like to get up to the dimension you're interested in. The fact that these two boardisms exist forces objects to have duals, and at that point it forces all of the morphisms to be invertible. And so this is incredibly trivial, but incredibly powerful result, because it means that if you just want to ask questions about the space of topological field theories, I mean, I would bet that this is true for quantum field theories in general, once somebody works out how to formulate them properly categorically. This is somehow a deep fact of physics, let's say, and it means you can just treat them as topological spaces.
Was a comment? I mean, Nito, would you like to unmute yourself and make your comment?
Well, I was just saying that there's maybe I didn't understand the question, your question. There are invertible TQFTs, and that's what I thought you were asking about.
Yeah.
And that's a different issue completely, because invertible TQFTs have one-dimensional state spaces. Here we're not talking about those things. We're talking about n-dimensional TQFTs creating a space of such. So the space of TQFTs of a fixed dimension n form a space. And invertible may be a different component, for example, in that space. So we're not relating the space of n-dimensional TQFTs with the space of invertible TQFTs. So I think it's two different spaces here. That's what I was trying to point out.
Everything you said is absolutely correct. If I say it in a mathematical way, the invertible TFTs, which by the way are just the classical ones, according to me, they are the ones which correspond to so-called invertible objects. So remember, my definition of an infinity groupoid was that all the morphisms are invertible. If you want to go and ask that there's some kind of notion of inverting objects as well, and by the way, you can only do that once you have a symmetric monoidal structure, which I haven't spoken about yet, then that is an extra layer of structure. And then if you just ask for the objects which are themselves invertible, then you get the so-called invertible topological field theories, indeed. So they should be thought of as a subset of the theories in this space. I have a big space X of all the topological field theories in, say, dimension D with a spin. And there is a subset of those which correspond to objects which themselves have duals or are invertible, and they are the classical field theories. And so they'll be the, or to say it another way, they're the ones which have a one-dimensional vector space.
Mm-hmm.
So let's say it this way, let's just look at one-dimensional topological field theories. As I said at the beginning of the talk, there is a theory for every n, and its vector space associated to a point is, say, Kn. I'm saying that all the morphisms between those theories are just the invertible linear maps. And there's a special subset of theories, which are the ones which are isomorphic to k to the 1. And they are the invertible topological field theories. So this is a completely different thing. And this is something which is true completely generally. So it's true at the quantum level. It's not a special thing of classical theories. Okay, so how do we now understand what a generalized global symmetry is? Well, what we do is we should just do what the mathematicians do. They split up the notions of group action, and a fixed point, usually thinking about abstract groups acting on sets. We just do the same thing, but we generalize them to generalized symmetries. So here's one way to think about a group. You can think of a group as an infinity groupoid, which has got just one object. It's got a single one morphism for each element of the group G. And you can already see that that has to be invertible because every element G of a group G has an inverse. And all of the higher morphisms, 2, 3, 4 morphisms, and so on, they're just the identities. And so that's a perfectly cromulent and completely equivalent way to think of what a group is. I just define it as an infinity groupoid with one object and one morphism for each G. What does that correspond to? If this is an infinity groupoid, it must correspond to a topological space. What is the topological space you get? You get the classifying space of G. Equivalently, you can think of it as the first Eilenberg plane space. Okay. Now, why do I make this perverse definition, equivalent definition of what a group is? I do it because it generalizes in an almost trivial way. So here's a definition of what a generalized group is. It's an infinity groupoid with, and rather than give you a long list of conditions like I did for a normal group, the only condition is it's got one object. So now, instead of just having non-trivial one morphisms, you can have non-trivial 2 morphisms, 3 morphisms, and so on. The only condition is that because it's a groupoid, they all need to be invertible. And so you can think of the 2, 3, 4 morphisms and so on as the higher Q-form symmetry groups once you've gone to the other side of homotopy theory. What do you get on the homotopy side? If you take this definition, you just get any connected space which is pointed. And where does that come from? It comes from the fact that when you only have one object in a category, that acts as a base point on the homotopy theory side. So a generalized group is this. It's a topological space which is connected and pointed. And it is a fact which I think originally goes back to Milner in the 50s, that in fact you can always write that as BG of some topological group G. And actually I think this is not necessarily a good way to think about it. In particular, this G is not necessarily unique. You could take any maximal compact subgroup of G, for example, and BG would have the same homotopy type. And there are some other reasons why it's not a good way to think about it. But if you're happy with topological groups, then maybe if you're happy with topological groups than you are with BG, then maybe it is a good way to think about it. Okay, so I generalized the notion of a group. Now I want to generalize the notion of a group action. So here's a perverse way of defining a group action on a set in mathematics. You can take a functor, which I'll call rho, from BG, considered as a category, to the category of sets. And you ask for that functor to land on a set of interest, let's call it S. And then the fixed point subset can be defined in the following way. You just take the limit of that functor rho. And so if you know something about category theory, you'll be happy with all those things. If you don't, well, you don't, but never mind. The point is that I can generalize again this definition immediately. Generalized action of a generalized group on an infinity groupoid X, such as a space of topological field theories, is an infinity one functor which lands on your space of interest. And if you take the limit, or rather the infinity categorical limit, you get another infinity groupoid, and it's the groupoid of homotopy fixed points. It is exactly this thing that I introduced before. You should think of it as a topological space whose points are topological field theories with G symmetry corresponding to the given action. And so what you've done somehow is you've taken the original space X and you've worked out all the ways that G can act on a symmetry, act as a symmetry on all of the theories in that space. Okay, and so you can unpick that definition. It's obviously very abstract. Basically what it corresponds to is that for each element in the group G, you pick out, so firstly you pick out a theory. And the second thing you do is for each element in the group G, you pick out a natural automorphism of that theory. That is to say an operation which commutes with all the dynamical evolutions, just like a symmetry. But the thing which is very general is that the group multiplication law only needs to hold weakly. And that's why you can get things like projective and antilinear representations out of this construction. But this thing is a direct generalization of the idea that symmetries are things which commute with Hamiltonians. They are things which are natural transformations, so they commute with all possible dynamical evolutions in the theory. So I think that's a very nice and close connection to what an undergraduate would define as a symmetry of a quantum mechanical theory. Okay, so I better hurry along because I'm running out of time. What do you need to do to compute all possible actions and all possibles on the homotopy theory side? Well, it's some sort of unpleasant calculation involving fibrations and sections of that fibration. These are all things which the algebraic topologists have known how to do for 40 or 50 years. So basically, if you can tell me what the original space X is, that is to say the original space of TFTs, the algebraic topologist can basically compute everything you want to about symmetries. And so actually the difficult part of this problem is to find X in the first place. And so in the paper, what we'll have is a complete discussion of one-dimensional and two-dimensional topological field theories with basically any structure you like on top of them, spins, whatever. Already to go to 3 dimensions and higher is difficult. It's difficult not because what this paper adds, which is the discussion of symmetries. It's difficult because we don't know what X is in the first place. Okay, good. So let me skip this as I'm running out of time. And so this just tells you, if you take, for example, one-dimensional topological field theories, then you can work out what all possible symmetries are. And indeed, you get the statement that I had before, that everyone corresponds to an automorphism of GLN. This is where we began the talk. And if you look at the possibilities, there are 5 of them, and nature uses at least 4. So it's satisfying to see that by doing this algebraic topological calculation, you basically get out everything, perhaps even more than you expect. Things get more interesting when you go to 2-dimensional topological field theories, because now you can have genuine one-form symmetries. And so perhaps what I'll do, since we're already getting to the end of the time, is I'll just explain what happens here and compare with some earlier observations in the literature and then stop. And so here's what happens. All you need to know to discuss all symmetries of these 2-dimensional topological field theories is you just need to know what the space X is, or rather you need to know what its homotopy type is. And that's a calculation you can do because 2-dimensional topological field theories have been classified. And so the answer is that basically the pi 0 is the positive integers. There's basically one theory for every positive integer n. The pi 1, which would correspond to, say, the naught form symmetries, are just the permutations on n objects for that n. And the pi 2, which would be the one form symmetries, would just be not quite rephasings, because phase doesn't mean anything when you don't have unitarity and you have an arbitrary ground field k. What you're allowed to do is you're allowed to multiply by arbitrary invertible elements in the field. And so that tells you basically, now you know what every symmetry of every 2-dimensional topological field theory is. And so it's interesting to compare with examples in the literature where people have studied generalized symmetries of two-dimensional topological field theories. So here's an example from the original paper. If you take the theory you get by quantizing Zn times Zn gauge theory, so this is the digraph-Whitman construction, then Gaiotto and company claimed that you can find naught and one form symmetries, which correspond to this group here. It's some abelian group whose size is basically fixed by the gauge theory you start with, the gauge group that you quantize, and also the action that you choose. And so what we find is that actually this is just a very small subgroup of the true naught and one form symmetries of the theory, which are these much larger ones here. And I think the main point here is to realize that studying theories by quantizing them, by taking individual theory and quantizing it, is a very bad guide to trying to understand what its symmetries are. Because if you want to understand the symmetries of at least topological field theories, you need to study the entire category, or rather the infinity groupoid, in one go, because that's where the symmetries come from. They come from the fact that you can do automorphisms of the theories that take one into another. And so if you just study classical actions and quantize them, sure, you find some symmetries, but you'd be very lucky to find all of them. And so what happens here is you just find a very small subgroup. And then the other thing which is interesting to compare, and in fact we had a talk in this seminar series about it, it was shown that if you take unextended, these are fully extended topological field theories. If you take unextended ones, which are nevertheless semi-simple, it was shown that the symmetries, the naught form symmetries correspond to permutations, and the one form symmetries correspond to phases. And once you know this result here for the fully extended theories, that comes as no surprise, because the semi-simple unextended topological theories are precisely the ones which can be extended to fully local field theories. And so the fact that they can be extended, this calculation up here already tells you what the symmetries have to be. They are precisely permutations for the naught form symmetries, and well, what the analog of rephasings is over an arbitrary ground field without a unitary structure for K. So let me skip to the end and finish because I'm out of time. I just wanted to talk about the gauging and ambiguities and anomalies. And let me pass to my closing remarks. So what I've shown is that if you take topological field theories, they don't have much dynamics, and so they're quite boring. But from the symmetry point of view, that's actually a wonderful thing, because every symmetry of a theory with non-trivial dynamics should already be present when you consider the theory with less structure, namely the topological field theory. And indeed, that's what calculations show. And the answer to what a generalized symmetry is of a topological field theory can be phrased in a very straightforward way. A generalized symmetry group is a pointed, connected topological space, and the rest of it, calculating what the symmetry does and so on, is just homotopy theory. And the last point I'd like to make again, and I think the example showed it well, is that this thing that we physicists usually do of taking classical actions of one theory at a time, or perhaps a few theories with a single coupling constant, which we vary, and quantizing them, it is not a very good guide to what quantum field theory is actually about. Unfortunately, for a long time, it's been the case that it's been the only tool we've got. But it seems to me that the developments that are being made on the mathematical side are actually getting us now to the point where we don't need to do this anymore. And so here are three disadvantages of doing physics this way. Disadvantage one, which we've known for a long time, is that it's not rigorous. Disadvantage two is that it doesn't work very well when things are strongly coupled. And you can see an extreme case, a topological field theory, there are no parameters at all that you can vary. So every theory is strongly coupled. And that's another deficiency that we've known about for a long time. But I think what this work shows is that there's yet a third deficiency, which is that if you really want to understand symmetries of quantum field theories, it's not enough to consider an individual quantum field theory and quantize it. You need to consider every quantum field theory, at least in some space of quantum field theories, in one go, because it's only by considering that space that you can see what all possible symmetries are. And so, like I said, I think everything I've said in this talk involves mathematics, which is either 50 or 60 years old in the case of the homotopy theory, or over 10 years old in the case of the cobordism hypothesis. And since then, the mathematicians have not been resting on their laurels. They have been pushing this further. And I think we really are getting to the stage now where there is the hope that we can talk about physical theories, i.e. ones with dynamical structures like metrics, using this kind of approach. And I think it will be really interesting to see what can be said about symmetries when we start doing that. Okay, so thank you very much. I'm sorry that I ran out of time, but...
Okay, thanks very much. It was a really nice talk. Other questions? People can just unmute themselves and ask questions, please. Maybe I'll start off asking the obvious question. So if you have a physical theory, say a quantum field theory in say 4 dimensions, and you would like to actually understand sort of the symmetry structure or the symmetry category of this, how is this work going to, lead us understanding that? So you were just making the point that we shouldn't be looking at the action for this and quantizing the theory, looking at topological operators, but there should be a better formalism. So what is it? What do you think is that for physical QFTs?
Right, so good question. And I think the answer is, like I said, the most difficult part of this computation, if you like, is to actually figure out, so you know that this space of theories is indeed a space, okay? And once you know that, you can apply all these tricks of homotopy theory to compute anything you like about the symmetries. Yeah. The thing which is difficult is to figure out what the space is in the first place. And there's even a 0th order difficulty, which I alluded to in my talk and which you pointed out to me when we were discussing in one of the early seminars about differential cohomology. The real big problem is nobody knows what the correct category is, or higher category, which extends vector spaces and linear maps, which is obviously the correct category, quote unquote, for doing quantum mechanics. And I guess the real problem there is that, the experimentalists, as always, are the ones at fault, because they're not doing enough experiments in which they compute correlation functions involving higher codimensional objects. If they were doing that, and perhaps this is a job for the condensed matter physicists rather than the particle physicists, they could probably tell us by means of experiments, just as we figured out that Hilbert spaces and linear maps were the right thing to do for quantum mechanics, they could probably tell us by means of experiment what this category was. Until we know that, then we already have a first problem, which is, what is your target category? And certainly there are sort of plausible guesses, and one can work with those, but I think it would be nice if either the experimentalists or we actually did some work on that problem. And then even when you know what your target category is, you still have the problem that you need to compute what the actual space is. And to compute the actual space, the miracle is the theorem says there is a space. The theorem doesn't tell you what the space is. And the difficulty is to figure out, the coboidism hypothesis is a strong theorem for what the answer is. It's just one which is not particularly useful. It tells you, you take your category and you take the so-called fully dualizable objects. But to find the fully dualizable objects is not necessarily an easy thing to do. Everything which has come in this talk, which is just a discussion of the symmetries and so on, that is all just homotopy theory once you know the answer to that. And so I think the next step, if you like, is to figure out, let's not do 4 dimensions because 3 is hard enough, that's the next one. The next step is to figure out what is the space of 3-dimensional topological field theories, which there already has been some work in the last 5 years on that, but I think it's not still settled. So there's this business of fusion categories and so on. I think that's the next big step. The part about including dynamical structures like metrics, the belief amongst the mathematicians seems to be that they still do form spaces. So again, the job is the same thing. You just need to find the space. And when I say just, it's a massive understatement. But once you've got that space, then you just do homotopy theory. And homotopy theory is a subject which is 70 years old, and somehow the theorem is, every single thing you'd like to calculate looks to be impossible to calculate. But in fact, you can calculate everything if you know enough tricks.
Okay. Thanks. Any other questions?
May I ask one? Maybe you said this implicitly, but I didn't catch it. So higher form symmetries come from homotopy groups, right? How do you model things like two groups in this framework?
Yeah, so a two group is, I mean, if you ask me for my definition of a two group, it would literally be a homotopy two type. It would be a topological space whose non-vanishing homotopy groups are just the 0, first and second one. And that would be my definition. I mean, this is, okay, so it depends what you mean by two group. And I suspect what you mean is if you look at various papers by, say, John Bayes about what a two group is, you'll find various constructions involving bicategories, and there'll be strict two groups and weak two groups and so on. One of the great things about doing things this way using infinity categories is that is all gone, or rather it hasn't gone, it gets done automatically. You know, all of those distinctions are just, you know, they are all taken into account automatically by the fact that you're working in the context of infinity categories. So as a strict two group would just be one in which it's a homotopy two type, which has got some sort of simpler structure in its homotopy two type. And the most general thing would just be a homotopy two type.
So does it include the type of two groups where you have a continuous zero form symmetry? Yeah, so this is the big problem is that as soon as you try to give these, so what one way of viewing what's been done here is, you know, that you've got this sort of tower of Q-form symmetries. And as long as you're willing to treat those as groups, as in not Lie groups, just as abstract groups, then sure, you can think of them as the homotopy groups of some topological space. And the point is that all of the structure that those generalized symmetries have, all the ways those groups can talk to each other, if you like, that is automatically incorporated in the fact that they're the homotopy groups of some topological space. The problem is, as soon as you say to me, well, I want those individual groups to have a smooth structure, then the whole edifice collapses, because there isn't a nice natural way to give a smooth structure to the homotopy groups of a topological space. And I'm sure that there are people who will tell you the right way to generalize that. I imagine it will involve things like stacks and so on. But basically, it is going to involve starting all over again. It's most definitely not the case that you can do some sort of tweak of what's been presented here and discuss symmetry groups. There's one thing which will actually be in the paper, which doesn't really fit in it, which is basically a sort of derivation of Noether's theorem for ordinary symmetries in topological field theories. Because you can ask yourself, you know, if you look at even the one-dimensional topological field theories, they have a symmetry which is basically GLN. And I've forgotten that GLN is a Lie group, but it is still a Lie group. And so you can say, oh, how can I give it a smooth structure? And then can I derive Noether's theorem in the rigorous axiomatic context? And the answer is you can, and we will put that in the end of the paper. But I didn't want to make a song and dance about it because I simply don't know how to generalize it to higher form symmetries. But if you like, it's the first step. And so Noether's theorem, which is the statement that you have some sort of, well, what's the statement? It would be that for each element in the Lie algebra, there is some conserved operator. You can formulate that in a rigorous way using topological field theory. So that's the sort of first step. Cool. You know, the statement that a charge is conserved basically corresponds to the fact that you can take any manifold, you can cut off a piece which is null bordant, and the value of a correlation function won't change. It's like the Ward identity. So that's already a nice thing, but I have no idea how to generalize it to higher form symmetries. And as I say, I suspect it will involve something like stacks. Or, I mean, it would be a nice thing to do, and I don't think it's impossible, but it will involve sort of starting again. Sagar, I think you have a question.
Hi. Yes, I want to ask if this classification in terms of the homotopy groups can be also mapped to a classification in terms of group cohomology instead. Yeah,
it can. So maybe the right thing would be to say, would be the following. If you want to classify all of the ways that a group, so the group itself is characterized partly by its homotopy groups. The generalized group is characterized partly by its homotopy groups, but actually there's more information, which is the homotopy type. The ways in which that group or such a group can act on spaces of topological field theories, the ways in which it can act are characterized by things which boil down to ultimately group cohomology. So that would probably be part of what is confusing, I think, about the physics literature is that these three different notions of a group, an action, and a fixed point are all blended into one in the physics literature. And there's a good reason that the mathematicians have distinguished the three. It's because it avoids confusion like this. And so I think the correct statement is that the information about the group itself is encoded in the homotopy type of the space, part of which is the homotopy groups. The actions, the ways in which that group can act on physical theories boil down to various things in group cohomology. And the same for the fixed points. I mean, if your question is a more basic one, which is, are homotopy groups related to cohomology groups? The answer is yes and no. They're related by the Hurewicz map. And so some of the information is in there, some of it isn't. Ultimately, the thing which is fundamental are the homotopy groups, not the homology groups.
So I want to go to the point that you made at the beginning. Well, I think you skimmed over it because you ran out of time. So you were saying something about there's an ambiguity when you gauge. So I think for you, this is like coupling to a background.
Yeah, so sorry, I missed that.
Yes.
Yeah, you're quite right. So
talk about this.
Let me find the relevant slide, but you're quite right. So, well, this one will do. So my point is that in general, the right way to think about an anomaly is that you have a space, which I call XG, of theories with a gauge symmetry, and it's a topological space. And there is a natural map, which you get given for free, which is just a continuous map, which sends you to the space of theories with global symmetries. Okay, and so the question of anomalies now becomes this. There are two things which can potentially go wrong if you start with a theory with a global symmetry and you ask if it can be gauged. The first is that this map simply doesn't land on this space at all. And that sounds a bit confusing. The reason it's confusing is because the notation misses out the fact that the information here is not just the group G, but it's also the way that the group G acts on the space. And so here's a classic example of how this fails. If you take, it's a well-known fact that projective representations in quantum mechanics can't be gauged, right? And so here would be an example. If you take any G and an action which corresponds to projective representations, then you are never going to be able to find a map which lands on that space. And so that's the first thing that can go wrong. You don't have a map at all. The second thing that can go wrong is that your map is not surjective. I mean, surjective in the homotopy theoretic sense, pi0 is surjective. So there are two kinds of anomalies. You can have exactly the same thing on the source side. You might find multiple maps from multiple different spaces which land on the thing you're interested in. And even if you only have one map, it might not be injective. So there might be, and so what I call an ambiguity is that there may not be a unique way to gauge a given global symmetry. And when I say may not, I actually mean in general is not, because we have examples of both of those phenomena. So an ambiguity is the fact that there are multiple ways to couple, to take a given global symmetry and couple it to background gauge fields. And somehow that seems to be something which physicists are not interested in. I don't know why, because from the mathematical point of view, it's, you know, it is the cousin of an anomaly.
Right.
And so somehow it should be interesting, and it happens.
Sure. Yes. Yes.
Can I ask a question, Ben?
Yes.
The two ways things could go wrong you were mentioning. Can you clarify something? It seems to me, in my mind, they are the same thing. They are both of these things are spaces, correct? XG in one side, XG on the other side are both topological spaces.
Yeah.
Correct. And they presumably the one on the right hand side has several components. And
yes.
And the point you're choosing is on one particular component. And what your first problem is that the map from the left to the right may not hit that component at all.
No, the first problem is simply there is no map. So perhaps we say it another way. If you start with a GX, a set of gauge theories, then for free, there is a God-given map out of it to some XG. But the theory that you're interested in might not be in that XG. If it corresponds, for example, to a theory with a projective representation in quantum mechanics.
To talk about the right XG, you need a G action on X.
Yeah, you say that the notation is unpleasant, okay. But the point is there's not just G in here, there's the way it acts. And the problem with gauge theories is that the way that G acts is largely forced upon you. So, I mean, I didn't talk about gauge theories. There's an interesting thing here, which is that you can have either internal gauge symmetries, or you can also have ones which actually act non-trivial on space-time. But still, you get a restricted way in which this G can act. And once you've got that, this map is given to you for free. I mean, let me tell you what this map is. Like I said, I mean, a physicist would call it setting the gauge field to 0. Here's what it is absolutely rigorously. You take a theory in here is defined on every space-time manifold equipped with every possible G bundle. You just restrict to the trivial bundles, you throw away all the other ones, and you evaluate your theory on it. And then you can do a gauge transformation, by which I mean an automorphism of principal bundles, and you for free get something in here. So that is what that map is, basically. It's a totally canonical construction. And so two things can go wrong. One thing is you just don't land on the right space at all. So that means that every single theory in your space is anomalous because you just can't land on it. The second thing is there is a map, but it's not surjective. It doesn't hit all of the theories in there.
Yeah, so that was what I was, that's the obstruction I was pointing to, the component obstruction.
Right, okay, and yeah, and then this point, which I think is absolutely key, because again, I mean, many of the things I'm saying here are known to the mathematicians for 10 years, but somehow the physical interpretation seems to be not known at all. This thing, the cobordism hypothesis, says the second one, it just can't happen if a theory is fully local. Because this map is basically, I mean, it's not an isomorphism, it's a weak homotopy equivalence, but that's in homotopy theory, the language that it suggests. So it just can't happen. And so many of these, I mean, I didn't mention it in the talk, but there's this whole literature about anomalies in two-dimensional topological field theories, which goes back to 7 or 8 years ago. If you look at this literature, I mean, I spent ages pouring through it and thinking, how can this be? These theories cannot possibly be anomalous. And the reason, the argument why those theories are not anomalous is because they're all based on digraph-Waffer theories. They're things you get by quantizing gauge fields. All of those theories are extendable. They can be made fully extendable. And then the cobordism hypothesis says there can be no anomaly. And so for a long time, it was a mystery to me what exactly was going on. If you read those papers carefully, what you realize is that those papers are about, they give a sufficient condition for a theory to be anomaly free. And what they call a theory with a Hooft anomaly is one where that sufficient condition is violated. But violating sufficient condition and violating a necessary condition are two very different things. And so, in my opinion, those anomalies, quote unquote, should not be called anomalies because they do not correspond to what everybody understands by a Hooft anomaly, which is a global symmetry which cannot be gauged. They are instead theories with a global symmetry which do not satisfy a sufficient condition for the global symmetry to be gauged. And so, you know, those kind of examples made it clear to me that there are things which are absolutely standard to the mathematicians, namely the cobordism hypothesis, and their implications for physics have not been assimilated by we physicists.
Okay, so I think we've now gone almost half an hour extra. Maybe we thank Ben again, then we stop the recording and then discuss more. Thanks a lot.
Thanks ever so much.
Talk. Yes.